Hi everyone. Our project's name is Categorization of Photonic Cavities for Quantum Applications. This is led by Dima Farfanek. And as outlined in the introduction, nanofabricated photonic cavities hold great potential for advancing technologies in quantum computing and communication and sensing. However, the fabrication process of these cavities is not always successful. There can be some factors affecting it, such as human errors or instrument malfunction or improper dosage selection. So, traditionally, identifying successful cavities involves high resolution imaging using SEM, but this can be labor intensive. Moving on to the background, photonic cavities play a big role in various quantum applications. And as I said, SEM can be labor intensive. So there can be a very big need for a non destructive categorization method, such as applying machine learning on low resolution images. Coming to the preparation of data set, we have prepared the data set by first manually labeling the each cavity in an image, and an image has 16 cavities. So we have done this using RoboFlow. In RoboFlow we have also used pre-processing and augmentation of data. We have also changed the size of the data to 640 cross 640 so that it's efficient and consistent for our machine learning model. And we have annotated the data using the fine centering algorithm, which fine centering algorithm mainly detects the center of the cavity in the image. As I said, there are 16 cavities in one image. So locating each cavity and centering it in the bounding box can be a hassle. So we made a fine centering algorithm to do this. This will be explained in further slides. Handing it over to Arjun for other presentation slides.
Thank you. So the initial idea was that if we could take the original full image, which is resized to 640 by 640 pixels, and pass that directly into CNN, that would be the most ideal, at least direct way to extract all 16 cavity labels. And so what we did was we wrote a CNN that relied upon a set of convolution layers, batch normalization, and some dropout layers to avoid overfitting. And we passed in the full raw image into that CNN. One note I should make is we used ELU activation functions as opposed to rectified linear units because ELUs tend to have more negative values, and so the idea was that we could try to limit the exploding gradient problem by centering the mean output roughly. Um, what we found though was that the raw data for the full size image was very, very large when loaded into RAM, around 5 to 6 gigabytes. And the second issue was that there was a lot of image centering variability, meaning that if I had the top left cavity that was supposed to be located at, say, pixel 50 by 50, in image one, that might be true. In image two, it might actually be in 150 by 150 pixels, and so on. This is a very variable choice as well. And so I think that that made it very difficult for our model to center onto any or to equilibrium to any single training loss. The other issue that ended up coming was that even though we had around 200-ish raw images with augmentation around 600 images, that did not seem to be enough to really sufficiently train our model, in addition to the high RAM cost. So there were a couple of things that we thought to do. The first one was using or to finding some way to compress our raw image into a lower dimensional space and then using our CNN onto that lower dimensional space. So to do that, we use a convolutional variational autoencoder where we try to use the convolutional layers to extract features, compress those features into a lower dimensional space, and then pass that latent layer into a CNN for classification. However, what we found was that that latent space had to be very, very large, more larger than we expected, in order for it to have any comparable performance with our full CNN compared to passing in even the raw images. And on top of that, the RAM cost was very high. I think in our case, it hit almost 16 gigabytes. What we also tried was we tried to use dimensionality reduction techniques to reduce the noise in the data set. Noise meaning like streaks of gray or streaks of green and so on. In that case, we chose NMF, and while that was helpful, they didn't really solve our RAM problem. So what we ended up doing was, as Xavier mentioned, was we decided to create an image segmentation and center search pipeline to constrain the size of each image into that of a single cavity. What we did was, We use a contour detection algorithm from OpenCV to find the edge of a cavity. We take the average of it, and we have some validation metrics we use to confirm the center found is likely a probable center. And once that is found, then we take that center and expand it by a finite size of pixels to create a 64 by 64 image of what should be just a single cavity. I'll hand it off to Akash to talk about the CNN model.
Thank you, Arjun. So we use the CNN model for our architecture, neural network architecture. So we had three convolutional layers with max pooling and the regularization function. So max pooling was mainly used for the spatial dimensional reduction of the images, and the layers were 32 and 64 and 128 layers, which we used. And then we use regularization methods like dropout layers to just prevent overfitting of the model, and we use binary cross entropy for the binary classification, and we trained based on this model. So moving on to the next slide, we can see we just built the basic architecture of the model. So here you can see three foundation layers with max pooling, and we flattened the layers, and then we applied the activation function softmax to train and test the data. So the results were quite impressive with 97% accuracy for the CNN model. So uh, it wasn't overfitting as the validation loss was quite consistent throughout the epoch, and this was the final result of our model. So, thank you.